Alejandra here today. She will be talking about the light we can see.
Said in such a mysterious way. So thank you for the invitation. I'm very happy to be back here. Although I couldn't quite remember precisely which was the last year that I was back here, but I'll make sure I'll remember. It's been a while. In any case, so today I want to tell you about a paper that I still don't have, to my embarrassment. I don't have an archive number yet, but it will come out soon. I do think it's bad luck to write archive year XXX.
It's only April.
Still bad luck. I think there's a curse when you do that, then actually it never comes out or something. In any case, that's just my paranoia. But it's work in collaboration with Luisa Polo, Susana Vintaya, and Diego Lisca. And I'm pretty sure very soon, in a few months, you'll all meet Susana, who will join this group as a postdoc. Okay, so let's get started. So what is this light that we can see? So this talk is about black hole physics, and in particular, the relationship between black hole entropy and modular forms. So as perhaps many of you know from different contexts of like understanding black holes in string theory and the origin, the microscopic origin of their entropy, modular forms have been incredibly important, okay? What I want to do is basically revisit this connection between modular forms and black hole entropy, and I want to tie it to new consistency conditions, with a new, more modern understanding of ADS-CFT. So basically what I'm going to do is revisit a really old problem and try to put it in a modern perspective, okay? So what is more concretely the type of black holes that I'll have in mind? What I have in mind are BPS black holes, extremal as well. Nowadays I have to specify both things, they're supersymmetric and extremal. And these are going to be black holes in 4 and 5 dimensions in ungauged supergravity. This basically means black holes that are embedded in flat space. And something that has been done, even it goes back to 2011, is that, okay, as we all know, the entropy of the black hole, the leading term goes like the area. There's also a logarithmic correction to the entropy of this black hole, plus additional corrections. But in particular, these the leading and this first quantum correction have perfect. There's a perfect agreement between this gravitational computation and a counting formula and appropriate modular form. This will still be true. I'm not going to change this part of the story. So I'm not going to tell you that something went wrong in this matching. No. The thing that I want to do, because I'm slow and I kind of like to understand things in a slow way, basically what I want to understand is what did we learn about the microscopic theory when we reproduce these corrections, the leading part and the correction? What did you learn about the CFT, if you wish? Okay, so that's the part that I'm kind of putting into this more modern perspective. And so let's review first a bit, how does a gravitational computation go about? Okay, so what do you do in gravity? In gravity, you have a big fat black hole, and for simplicity, let's assume that it carries some electric and magnetic charges, Q and P here, okay? And so what people do is basically, they think of this from the Euclidean perspective. We're going to compute a gravitational path integral as a function of these charges that the black hole carries, okay? So as you compute this, you do a saddle point approximation where there's going to be a tree-level answer and a one-loop correction around the saddle point. And what the validity of this expansion basically requires for you to take the charges to be very big. So it's useful to introduce this parameter lambda that tells you how big the black hole is, how it scales with its parameters. So in order to be mindful with the units, and here I'm also doing it for any dimensions, but we will look at 4 and 5 dimensions. Basically, you scale the charges in this way. The area of the black hole will scale with this parameter to the b-2, and this lambda is something very big. So it's a big fat black hole that is dominating this. And in this regime, you basically can compute the leading part, the area law, and this logarithmic correction that basically comes from this one loop point. In particular, this logarithmic correction has two components to it. One is a local contribution directly from heat kernels of massless fields running around loops. Okay, so you need to know what is the massless fields that your theory has. And there's also a part that comes from zero modes that are basically the isometries that the background has. Okay, so if you have a killing vector in the background, or if there's zero modes in your one loop determinants, you'll get contributions that we usually, just refer to as that. Okay, that's the gravity side of the story. I'm not going to say much more than that to the gravitational computation, but if there's any questions about this, I'll ask. Please ask. Now, what happens from the microscopic point of view? So what are you computing? So usually here's where the modular form enters. So here I'm writing a modular form that will depend on two variables. It's going to be what I'll call very soon a weak Jacobi form. And basically this is something that counts BPS states. From the microscopic point of view, this is something that you should associate with something like trace -1 to BF. Okay, ... depending on theories and details, but basically it's an index. Okay. Now, something in this formula that is very robust, dictated by modular invariance, is that the coefficients of this modular form, usually there's always a regime where they will have an exponential growth, where these parameters here that I'm calling delta and delta naught is what we call the discriminant of the form. So it's this combination of n and l that enter that control the degeneracies, and this delta naught is basically what we'll call the maximum polarity state. If you like to think of it in the CFT language, this is minus C over 24. Okay, it's like the Casimir energy that the system has. Okay. Now, a lot of the hard work and things that are important is to basically match what I mean here to the parameters that I have here in this board. Okay, so there's a non-trivial. And as we go through examples, we'll see how these two sides are matched. But basically, the short story of this is that you compute the logarithm of d. It will give you this expression. And the observation is that the two quantities agree. Okay, so the logarithm of this of these Fourier coefficients here basically match this expression here. Okay. That's the version of like how we basically understand how to reproduce the the Bekenstein-Hawking entropy from the microscopics. But now to refine more my question, basically I want to understand what is the microscopic information that controls these logarithmic corrections here. Okay, so what did I learn about the CFT? What is the information about the system, the microscopic system of this index that control these two corrections? And in particular, I want to understand if extracting this information here was something that was just dictated by symmetries, or if there was dynamics in the match. Okay, so with that in mind, we're basically going to, most of the talk, the majority of the talk is just going to be focused on this microscopic side. I want to understand basically these steps and how to get to those two coefficients. So what I'll do, basically, I'll first tell you a story about how to extract these coefficients D and L in a very general and generic way. I'll tell you about how to implement holographic conditions. So this is where ADS-CFT is going to come in, and what's known as the HKS bound. The method that I'll use to extract the coefficient goes under the name of crossing kernels that I'll define very quickly. And then, because you might not trust me, for reasons that will become clear, you will look at me with a skeptical face. It's like, what are you doing to these modular forms? It sounds horrible. You're a butcher. I will agree with you. So we did our homework and we looked at a certain class of modular forms that are related to symmetric product orbifolds and exponential lifts. And this gives us, we have other methods and other techniques how to extract the coefficients. And we can see that at least there's something meaningful here, that we got the same corrections, and we can also understand what the origin is. Okay, so this is basically your reassurance. Also, these cases are relevant for the explicit examples that I'll describe. So these are modular forms that enter in the microscopic match. And then the two examples that I'll discuss in the talk are basically quarter BPS black holes in equal to 4 and equal force of gravity, and quarter BPS black holes in equal to 5, the BMPV. Those are the two examples that I'll present to you. You'll see there, if you're still with me, you'll see why I picked those two examples. Well, there's many reasons, but I think that it illustrates really well basically what's going on with these coefficients in those two cases. Okay, so they're quite different. Okay, so let's get started then and start talking about the asymptotic expansion of this DNL. So I'm focusing just on weak Jacobi forms. You can do this for some other classes of forms, but this is the one that I have a lot of control, and it's the one that is naturally related to an index. So I'm going to look at this class as modular form. So what is the core properties of it? So basically, so as I said, they have two parameters, complex parameters, tau and set, and they're basically defined by their modular properties, where the forms generically will have a weight, and they will have an index here, T and K. And they also have elliptic properties, also known as like spectral flow transformations. So if you shift set by tau, basically the form transforms in this way, okay? So from the point of view of number theory, these are two defining properties of weak Jacobi forms. What makes them weak is that this integer n is basically positive, okay? Now, the way to organize these states, as I already introduced, I introduced this concept of the discriminant. So this is basically a quantity that is invariant under this elliptic property. So you can think of the coefficients as a function of n and l, but sometimes it's convenient to think of them as a function of delta and L mod 2t. We'll mostly just focus on the delta dependence, which is the most prominent one. And as a function of delta, you split the states into two. So if the discriminant of a state is negative, you call it polar. And I will also equivalently call it light, a light state. And if the discriminant of the state is positive, I'll call them non-polar or heavy states. The light and heavy is my trickling into ADS CFT, okay? But if you want, just from the mathematics, you basically have polar states and non-polar states, okay? And the state with the maximal polarity is this delta 0, which is basically, I'll characterize it as minus an integer b squared over 14, where this integer b has to be less or equal than the index, okay? So that's a condition on it. So you can have the maximal polarity basically is this delta naught here. But again, if you want to think of it in terms of the CFT, you can think of it as the Casimir energy of the system, minus C over 20, roughly speaking. Okay, now for these modular forms, there's something quite remarkable. And it's that the Fourier coefficients of these forms are just known. Okay, this goes under the name of the Rademacher expansion. So you want to know what you specify with Jacobi form, you want to know one of these coefficients, here you go. This is an explicit formula. So the output here is basically you're looking at the Fourier coefficient of a non-polar state. And this is basically controlled by two things. It's basically controlled by the polar states here. So here I have a sum over the coefficients again, but only when the discriminant is negative. And then I have a bunch of stuff here that are known functions. Every funny symbol here is something that is explicit. So I have this polynomial part here. This is a Bessel function. This is called a Kloosterman sum. That is basically some phases that you haven't. And from these known functions, actually, it's where you can see that if you take large values of delta, this Bessel function goes exponentially, and that's what gives rise to what I wrote in a few slides back, that these coefficients grow exponentially, okay? That's it. Now, so here I have an exact formula. So I'm done. So now we can, so I know everything that I need to know about the modular form, but I'm stubborn, and I'm not going to use this.
You didn't really say why n had to be a positive integer.
Which, sorry,
In the very definition,
no, you could, because I said weak, so that's why if you say weak, then N is positive. So if I
third week was usually there's a lower bound on how negative it could be. No?
that also, but so it's combined. The two things are combined. So if you want, it's a little bit of the chicken and the egg, which one you want to state first. I'm kind of following Sagir here. And so he first starts with saying N is positive, and then you can still have states with negative discriminant up to that like maximal polarity. But sometimes I know that it's a little bit more intuitive to say you allow for states with negative discriminant, but N is still strictly positive, because you can also have Jacobi forms where N is negative as well. So if you think of this, like, so this is like the Ramon sector computation. So then N is always positive, but if you if you do a half integer spectral flow, you go to NS and then N is negative. But then from the mathematics point of view, that's no longer a weak Jacobi form. It's a meromorphic, no, what they have, that's not quite narrow. But okay, they give it a different
physically,
name.
why should N be positive? That's sort of my.
It's, I'm doing this in the Ramon sector, that's why. So in the Ramon sector, the lowest state basically starts with a power of Y. And then the Q expansion is all positive.
So it's CFD. I mean,
Yeah.
it's two-dimensional.
Yeah. So, but a lot of what I'm saying though, and then I will use properties of the ring associated to the Jacobi forms, to the weak Jacobi forms. But again, especially these crossing kernels that I do, that they don't care that I'm using weak Jacobi forms or not. You can have N negative there, and everything that I'm saying is going to go through. It's mostly when I go into the symmetric product part, and I'll tell you why I'm doing it for weak Jacobi forms when it comes through. But this part here, yeah, but okay. Yeah, and then also in my head, like going to N negative is like just do a half integer spectrum in my head. That's how I would do it.
Sorry, I'm not an expert on this, but like, is there any interpretation of this, like that you get some like heavy data from like just summing over light data? Is there any like physics you can
That's what
associate into this formula?
I'm trying.
Okay.
I'm trying. This is the part that I want to understand. Like in some sense, another way that you could have asked the question that I asked at the beginning is how does gravity emerge from this? Like what is it? Why do I look at this formula and I think gravity? We don't know yet. We know in some examples what is the physics in this, but like if you want from the CFT point of view, this is basically the modular bootstrap. This is telling you that the S transform always relates light states, like basically low temperatures to high temperatures. It's a version of that. So this is, from a CFT perspective, this is what modular invariance, how it constrains the spectrum and its fullest. And here you're using full SL2C to understand how heavy operators are basically dictated by light, by the light operators. So it's the most extreme version of the bootstrap. But in general, like I'm interested on the gravitational side of this interpretation and understanding what did I learn about gravity and what are the rules that I need how do I need to massage this such that I can see a black hole from this. And there's certain hints, and if you want, the first one is this exponential growth in the Bessel functions that hints to you that this looks like a sum over saddle points, which each saddle point basically having this exponential factor here, and there's the most dominant one that has C equal to 1, and then subleading saddles with lower values of C. So that this part here is hinting to you to like a saddle point approximation. That you can then think, path integrals are also friendly to saddle point approximations. Any other questions? Okay. Okay, so, but I'm not going to use this. I'll refer to it and I'll make some comparisons, but I'm going to be mediocre. And the reason why I'm going to be mediocre and not explicitly use this formula is because when we are interested in doing gravity and doing either holography or black hole physics, the situations there from this perspective are very coarse. And what do I mean? So when I was scaling parameters like these charges, making them large, T, the index, is one of such. If you translate it to gravity in the examples that we know, the index, which basically will control the central charge of the system, is something that also scales. So we always say like, you're taking a large central charge limit, a large n limit. And so you have to think of this parameter T as something that is a continuous parameter, and is something that as you look at how the black hole responds and reacts, this is one of such parameters. And it will affect basically also the logarithmic corrections as I tell you how it works in the examples. And the issue with this is that if I look, for instance, at this part of the formula, you get a little bit like nervous. I don't know how to extract scaling behaviors in T if T is controlling the ranges of the summation. This is just I just might not be as a good mathematician as I wish I was, but I just don't know what to do if T enters there, because you're asking me to scale over T, and then these log A parts are controlled by things that basically have log T terms in them. So this is basically where I'm like, okay, this expression is beautiful, it's exact, but not quite useful to match it with this coarse picture that the gravitational arena is giving. So how do I do a more mediocre job? So the way that I do a more mediocre job is that I'm going to start introducing this concept of crossing currents. So in this sense, a useful way how to think about the problem is that instead of thinking of these coefficients as being discrete, so I wrote before the weak Jacobi form as a sum over n and a sum over L, let's treat these variables a bit more like as continuous variables, okay? So let me think in terms of like energy and a variable J here. Now, of course, if you want to reproduce the modular form that you had, these are actual distributions, okay? So they're delta functions that are supported on the integer values that you had, okay? But for a moment, let me think of this as basically just like, okay, there's a density of states instead of thinking of discrete Fourier coefficients. And from that point of view, then you can say, okay, let me, instead of Rademacher, use the full modular group, the full SL2 set to extract the coefficients. Let me be, again, more mediocre and just do an S transform. Okay, so just use one element of SL2 and see how far you can get in telling me something about the coefficients with just doing basically tau going to -1 over tau. And so if you do that, then you will get an expression for the density of states at E and J in terms of densities of states at A prime, J prime, basically multiplied by what's called, this is what we call the crossing kernel, okay? And this crossing kernel, you can solve for it. It's an explicit function, and it's basically this here. And you can see from here that some elements are already very similar to the elements in the Rademacher expansion. So you again get, for instance, this Bessel function, and you get this polynomial part that you have here. And if you, and so then basically by comparing what kernel you get here compared to what you get in the Rademacher expression, you can basically see that like how you would be off. So if you do this for the heavy states here, oh, sorry, I should mention one thing also here in this formula. So in this formula here, I do have to be a bit more careful, and this is only because I'm using just one element of SL2 set. What you put in here is not necessarily the light spectrum. So when you apply this, just the set transformation, this is again an integral over the whole spectrum. So it involves both heavy and light part of the spectrum. So which is the fallacy of the approximation, right? Because you should be constraining more with all the other generators of SL2 set, but if you just use one, it doesn't tell you immediately that you're looking at the light part. Now, if you put here that both states that you have involved have positive discriminant, then these Bessel functions are oscillatory, so they don't dominate. But if like the delta prime is negative, then you get this exponential growth again. So that's how you understand basically the contributions from different parts. So what I'm writing here, for instance, is like, let's say that you're interested in the density of states for heavy states, and you just take into account the contributions from the light states, which will give you the Bessel functions with the exponential growth, and the dot, dot, dots is basically other states that I'm neglecting. Then the ratio between these two things is basically 1 plus things that are exponentially suppressed. So this is where I'm losing information and things that are going to be exponentially suppressed. Okay, so we're going to carry on with this expression for the density of states. So, okay, very good. So I basically have this. So I have the D is basically, I'm going to approximate it by this density, rho H. And what we've seen basically is that this goes like the sum exponential of delta times the absolute value of delta 0. And this is basically something that is valid, like for me to feel confident writing this part of the expression. You basically just need the delta to be much bigger than delta naught, okay? This, if you go to a canonical ensemble, this means that you're in a high temperature regime. And it's what usually you know as the Carty formula, okay, for the density of states. Also, another thing is that these approximations tend to be very good also because you tend to fix the central charge, like the value of T and delta 0. And so then the big values of delta for which this is true, like they tend to not be that big. But now this is where I need to incorporate gravity, okay? So this is not quite what I need if I want to make contact with black hole physics. So for black hole physics, I need to have this, what we colloquially call like this large N limit. I need large central charges. And this basically means that I need to have access to a regime where T and delta naught basically go to infinity. They're very big. And the black holes usually, in the most common cases of holography, they happen to have a lot of entropy, have this exponential growth, not in this regime, but they tend to have a lot of entropy. I have to justify why you have a lot of entropy, even when delta is very similar to delta naught, okay? So the tricks that get you to the Carty formula are quite not enough, okay? So you can't just explain black hole entropy by saying that you matched it to the Carty formula. So this was already answered. This is not new to us. And so it was answered back in 2014, what I was calling HKS, that stands for Hartman, Keller, and Stoica. They said, okay, you want to have this type of behavior at intermediate regimes. So basically when delta is similar to delta naught, well, you have to put a restriction, not any light spectrum will give you that. So if your light spectrum is bounded in this way, so if it's less basically than less or equal to Hagedorn growth, then you will be able to justify why did you get an exponential growth like this in a regime for which delta is basically similar to delta 0. It can also be much bigger. That's also perfectly fine as well. But it allows you to write these expressions with confidence in this regime. Okay. And so what's going to happen next is that now what we're basically doing is saying, okay, let's combine this perspective of the crossing kernels, where we write down the density of states in terms of this light spectrum, with this sparseness criteria of HKS. And now the reason why I like this is because now this is going to be a function, and then I can think about like, okay, what type of light spectrum basically affects not just the leading part, but now the sub-leading corrections. And what we find is that there's basically two categories. So first, there's the universal regime, the one that originally HKS thought of, where delta is basically just a bit above delta 0. And so they established this exponential growth, but then you can also compute the sub-leading corrections to it, which I've written down here. So if you take a log of D, this will give you basically the logarithmic corrections. And what's interesting here is that a reason why I'm not telling you anything about rho light, besides the fact that it satisfies this criteria, is because the logarithmic corrections are not controlled by it. The only thing that can enter, and that's what I'm illustrating by the symbol, is that the ground state degeneracy is the only thing that could have affected the answer, okay? And we usually put that equal to 1 but I'm going to ask you please to not put it equal to 1 because we'll see that it will become important. But nothing else about the light spectrum, about these polar states was needed in understanding what was the first subleading correction. Now there's another regime that is a little bit more awkward, but we will see why it's relevant in black hole physics. There's a regime where you can then take delta naught to be bigger than delta. Okay, so let me just swap the roles of them. So the central charge is bigger than the energy. And there, the expression becomes much more complicated. There, you actually also have a more stringent requirement between delta and delta naught. And then the light spectrum does enter quite a bit. So these parameters that I have here, this omega and alpha, are basically dictated by what is the behavior, the asymptotic behavior of the light states. So W is basically, it will form like a weight of the state, and alpha is an exponent that goes up here in the exponential. But this is only true, well, I have to have this parameter alpha that is up here in the exponent, actually strictly less than 1. So these equations are not valid if you have a Hagedorn growth of states, just an exponential growth. You have to be below Hagedorn. Okay, so this is the information that we get from doing crossing currents. So now let's move on to putting this to a test. So let's look at symmetric product orbifolds and exponential lifts. Okay, so we had this Rademacher expansion, and I was whining to you that I would not use it, and I needed something that allowed me to be coarse in the way that I wanted. But there's actually another way that you can treat T in the same footing as N and L. What would that other way be? Well, in some cases, if you can tell me what would be a sum over T, so just treat T as another quantum number and associate a Boltzmann factor to it, then that's another way how you can treat this variable as a statistical variable, okay? So I'm just defining for you now a grand canonical partition function. And this is a great way how to treat variables that are discrete in terms of continuous. This is what you learn in thermodynamics, right? Now, of course,
Sorry, just to make sure, the increase of T, that growth is not separate from the growth of the charges you want to do when you.
it depends on the.
But you can't sort of take T large and fixed and then examine.
No, but sometimes there's still hierarchy between them. At least in the specific black hole cases, there's still a hierarchy between them. You usually take everything large.
But I'm asking why you're saying it's hard to work with the Rademacher expansion, but I can't because of the T. But it's not valid to take T large but fixed and then look at the asymptotics there. That's not.
But I can't extract the logs. That's I still find if you know how to tell me like why do you get a log T out of there, that would be great. I just don't see it. Like if you just want the very, very leading part, that was fine. Because you can just say, well, yes, sure, T is large, and then but it's just the Bessel function that is like doing the job. But then yeah, we know that the answer, as you will see in the examples when I had this non-universal regime, I really don't know how to see that from the Rademacher expansion. I absolutely, like the formula that I showed you that perhaps was not super illuminating, I still don't know how to get it from Rademacher. The universal one, you could have guessed it. You could have said, well, sure, T is big, but like at the end, it's just the ground state. So it's still just the first term and the Rademacher sum that is the important one. And we're just justifying it from a different perspective. So for the universal regime where the energy is comparable to the central charge, yeah, we're just making you feel warm and fuzzy inside that the intuition is correct. For this non-universal regime, I truly don't know how to manipulate those terms. But yeah, indeed, everything is large, N and L, like everything is growing. But yeah, the scaling properties of those formulas are just difficult to extract. But okay, so here I'm going to propose something a bit different and say, okay, let's try to see if there's cases where you can actually think of this in this grand canonical way. And there's two examples, and usually people don't do this because you don't know what a good family for this is. So you need to have like some rule of what you're summing over. And so that's why this is not the most trendy thing to do. But in string theory, it was called third quantization. And so that's why these examples also show up in the context of string theory. So basically, one example is symmetric product orbifold. So when we describe these theories, which basically here I put, if you don't know what this is the quickest definition of what a symmetric product orbifold is basically you're tensoring n theories and modding by the symmetric group. And what you do here is basically construct a generating function where you're summing over the number of copies n. Okay, so here, that's also why I was calling this a large n limit. So it's like the large number of copies that you have. Okay. And so this is basically your grand canonical partition function, and something that was very nicely showed by Dijkgraaf, Moore, Verlinde is that the sum also has an interpretation in terms of products. Okay, so and this product formula gives us quite a lot of control on how to extract information about the modular form. There's another procedure that you can do that is called an exponential lift. It's very closely related to the symmetric product, but formally it is a different modular form. It has a weight associated to it, and basically, so you grab. And this I only know, the mathematicians will only tell me how to do it for weak Jacobi forms. So here, their theorems and their properties, they very clearly state, give me a weak Jacobi form, and then this is true. And so basically, if you want the definition of the exponential lift, it's this product formula where here you have the three different variables, and the powers that show up here are the coefficient of what you call the seed theory that you had, or the seed form that you had. Okay, so these are two examples, and they're going to also show up as we compare to the black holes and the countings and string theory. Okay, so let me just to illustrate the method, I'll focus just on the symmetric product. The exponential lifts goes very similarly. So basically we have these formulas, and what I want to do is extract this coefficient. Then now it will be a function of n, m, and t. Okay, so that's what we want. This thing, the way that you can do it is basically to use, so you basically need to integrate set. Okay, so you need to do the Laplace transform of the sum. And where we're like, and the core of the method is to make use of basically the poles of this function. So it's contour integrals. So I'm not going to use crossing kernels. So if you did not like that part of the discussion, this is a completely different way how to carry out the computation. So you do about, you basically just use Cauchy's theorem. And so the result of that, here I wrote it. So this D, now here, basically now I only have an integral over two variables. So I integrated over sigma over the poles. The dots are other residues. So you have to identify which is the pole that dominates the most, for which you make use the delta times delta naught is very big. And then the subleading corrections are those other poles that have less contribution. But in any case, you can keep track of them. And what's interesting about this formula is many things. So the first thing here is that this part that shows up here is basically rho light, but when n goes to infinity. So this is something that you can show. It's not obvious from the equations, okay? So it's not like, oh yes, obviously, that's the number of light states when n goes to infinity. No, but back in 2019, for different reasons, we basically showed that this residue that shows up here is basically the light spectrum of the symmetric orbifold at n equal to infinity, which is kind of interesting if you think about it also, that here I don't have to take, so n is hiding inside of this product, but I don't really need to take n to be large. Like I could have just been doing the normal Cardy formula where delta naught is fixed and delta is big. But what this contour basically tells me is that it's always useful to think of like the relevant contribution to be the one when n was infinite. Although you can put here, so T and N are basically, they're proportional to each other. This formula still also works if T is finite, okay? So it's a number of light states. It's kind of interesting that it's a number of light states when N is infinite. Now, some other parts of this formula. So this little piece here is what I was calling rho zero of delta zero, the ground state degeneracy that I was pointing in the previous formulas. And this is basically coming because if in the seed you have a degenerate ground state, you can distribute that ground state. It's a Ramon ground state. You can then distribute it among the different N factors. And so here you can see that it's not smart to set this equal to 1. So you get an N dependence basically from the number of ground states. The number of ground states is scaling with N. Yeah, this other part here, if you want to think about an example in string theory, let's say if you're doing ADS3 times S3 times K3, this is basically the quarter BPS states in that case. Those are the light states that you're counting there. But more generally, you don't have to just look at that example. We do have a complete classification of behaviors of these forms. And basically, in terms of this notation of rho light, you can have weak Jacobi forms that give you Hagenberg growth, and you can also have weak Jacobi forms that give you 1/2. And these are the only two possibilities within the symmetric product orbifolds of the type of growth that you can have for the light states.
So what that's by infinity. So
I'm calling it infinity because N was going to infinity, but it's the residue. From doing the contour integral, you find it as the residue of this product. So the poles are basically when 1 is equal to this for non-trivial values of D. And then you just see what you get in the exponent as you expand out the form. Yeah. But usually people would have just called this. So in the old story, if you're familiar with it, people would just have said, this is the residue. And in an example that I'll use later on, it was interpreted as like bound states of a half BPS diones. Like it was associated with walls of marginal stability and things like that. But more broadly, it's in this language of ADS-CFT, these are basically, it's a perturbative part of the gravitational spectrum that you're, or the light part of the CFT spectrum that you have there. Okay, and so to keep the story short, since I don't want to hold you on forever, you can then further decompose these integrals, do saddle point approximations, and I just want to tell you whatever I told to you in the universal regime holds for the ones that have slow growth. You do the non-universal regime, it also holds. Okay, so I'll not show you those steps, but these formulas are completely compatible with what we got from the crossing. Okay, so let's get to black holes, because I guess that's what you'll like, black holes, right? Yeah, okay. Okay, so let's do this. Okay, so again, we have these two sides of the story. So there was this gravitational path integral where we have these log corrections. And what I told you from this side, from the microscopic derivation, was that it was important for me to impose this sparseness condition. We got to a formula like this, where there were two different types of regimes. In the universal regime, you only need to know what the ground state is. In the non-universal regime, you need to know quite a lot about the light spectrum. Okay, that's what happened so far. So okay, so let's start with D equal 4, N equal 4, quarter BPS black hole. Okay, so this black hole has basically an electric charge vector and a magnetic charge vector. And the area in terms of these charges, here I wrote it explicitly. So A over 4 is pi times the square root of that quantity. Okay, that's your area. And so the scaling here is basically Q goes to lambda, P goes to lambda. Okay, now people computed this logarithmic corrections from the path integral. There's a non-trivial contribution from the local fields that looks like this. This is written in general for any supergravity that has some number of supersymmetry, some vector multiplets, and some hypers. But okay, you put the the matter content, you put n equal 4, and in n equal 4 theories, you have this relationship between the number of vectors and the number of hypers. And the answer that comes from the local field is -1. The answer that comes from the zero mode. So here I split it into this because this is what comes from the killing vectors, and this is what comes from the fermionic zero modes, and it adds up to 1. What is -1 plus 1? I'm just testing if you're still with me.
0.
Thank you. It's 0. And so let's obsess about 0. What is the microscopic origin of 0? This is how it all started. What did 0 mean? Okay, so what did 0 mean? So in this case, this black hole, the microscopic formula is called, it's basically the exponential lift of -2 times phi 0 1, which is 1 over phi 10. It's called the Castro form, doesn't matter, but this is the modular form that you're using, that was used in the past. And so here I wrote how everything about the black hole is related to this notation of the Jacobi form. Okay, so it's a case where T is equal to B. This delta 0 is -q squared over 8. So you can see here that if Q is big, delta 0 is big, okay? N is P squared, L was Q dot P, okay? So you look at what is 4 pi square root of delta times delta 0, that same square root there, okay? Area, and that thing matches, okay? Strominger, Buffett, whatever favorite author you have, okay, there you go. Area matches. Now, because we look now here at what happens to delta 0 versus, let's say, n. Both go like charges squared. This means that delta is very similar to delta 0. So this black hole falls into the universal regime, okay? And so actually what happens in this case, you apply the formulas that we had, and the only thing that you needed to know was basically that this was basically rho naught. That's the part that I'm writing here. And you just needed to know that this power here that came from the exponential lift was actually 2, which is the number of remote ground states. That's what you learned from the CFT. If you would not have put this thing in here, you would have gone that you had a logarithmic correction that went like 1 over delta. And that's not 0. That would have been log of -1. Okay, so it was important for the match that you just learned that there was a degenerate number of remote ground states. That's what you learned from this exam. Okay, so it's mostly controlled by symmetries, and this is the only thing that you're proving about the CFT. What is the number of remote ground states?
What can you see? Like there is this symmetry between the magnetic and the charge vectors. Like there's a delta and not an n. There should be some symmetry.
Yeah. So this is also how this form was guessed. So here, this is called electric magnetic duality in 4 dimensions. It's part of the U-duality group in 4D. Historically, that's how people noticed that. Well, okay, they did their homework and they did their brain systems and did some things, but they were very guided into like understanding what is a modular form that will have this exchange symmetry. And the Castro form has this exchange symmetry. It treats N and T in the same footing. So it actually, it's part, so this form, it has modular properties, but it's actually bigger as part of SP4 set. And in SP4 set, you can exchange basically these two things.
And also, when you say, oh, they guess this form that is the correct one.
No, this is this was derived.
Index and like you have the theory, you should compute the index.
Yes.
That theory.
Yeah, and this is and I'm stating here that that's when you
there's
compute.
no guessing.
No. There's no guessing, but I wanted to know what did I learn about the theory. So, like, did I learn something that was like basically controlled just by symmetries? Was this guaranteed just because I kept on doing my tricks of modular invariance? Or was there something, what is the microscopic data that is affecting this? And so the logarithmic correction, so basically the exponential is guaranteed to you because this form has the property that it complies with HKS. So its light spectrum is below Hagendorn. So that basically, from that perspective, I say, this is why this form, I could write down this leading exponential term even in this regime. Now, the logarithmic correction, what went into it? Well, the only thing that went into it, after you determine what the regime is that this number here was 2, which is something that you identify as basically also CFT data. So the CFT line behind here is something that has 2 Ramon ground states because it's a 4,4 theory. So it just comes from the extended R symmetry. So I'm basically just giving it that light of like, how do you view this in the context of ADS CFT? What is the data that you're probing about ADS CFT? Okay. Okay, so now second example. So let's go up 1 dimension. So let's go up to 5D. And this is the BMPB black hole. So this is a black hole that carries 3 charges, Q1, Q5, P, and angular momentum J. Okay, so then the scaling of parameters is in this form. The area of this black hole is basically 2 pi Q1, Q5, P minus J squared. And then you compute the log corrections. And what happens in 5D, which happens in any odd number of dimensions, is that the heat kernels, this local contribution is always 0. You don't care what the massless spectrum is, you're always going to get 0. And so the only origin of a logarithmic correction from the gravitational point of view comes from basically what are the symmetries that you have, okay? And so here I wrote the number, so this basically depends on the number of vector fields. Again, there's a part that comes from the graviton, and this comes from the fermions. And then if I do this, so for the counting formula that I'll do is basically type 2b on K3 times S1. The number of vector fields is 27. And that's up to that number giving me -4. So let's obsess about -4. So in this case, the appropriate microscopic derivation comes from looking at the symmetric product overfield of K3, okay? And now let's look at how parameters scale. So here delta naught, which is the central charge of D1, D5, goes like Q1, Q5. N just goes like P. L is J. So then again, you do you see how this combination translates to the gravitational variables and agreement, fine. But now I'm in the non-universal regime because these 2 things, each Q goes like lambda squared according to this, but then, so this will go like lambda to the 4th, that's what I'm writing here, but then delta will just go like lambda squared. So this is also applicable to the Strominger-Vafa black hole that we all love. Okay, you are computing the entropy in a case where the central charge is basically much bigger than the energy of the system. Okay, and so now I need to use my more complicated formula that here I simplified for this case that I have here. So here I have the exponential growth, and here I have the corrections. But now I need to know information about the light states. So I already put in these formulas that the power here was 1/2. I need to know what that weight is, what that W. And basically this part here is the same as in the previous slide. So again, it's like 2 Ramon ground states because it's the same CFT. And the weight here is -3. And this D0, 0, 0, so this is another number that enters in the form, is basically 20, which is the data for K3, okay? And both answers now will agree. But I do want you to appreciate what's going on here. So from the gravitational point of view, it looked like the computation was trivial. It's just like zero modes, like really like, okay, there's not much that is happening from the point of view of the solution, but from the point of view of the microscopics, it's quite a lot of like data that you need about the light spectrum to get the match to work, okay? So this is where you should be impressed that you got the right microscopics because many things could have gone wrong. You are really tampering to information that is not obviously trivially related to the gravity part. And I wanted to highlight this 20 also here, because that 20 is this one here, but you do have more vector fields in the other side. So there's quite a lot of moving pieces that make the two result agrees. Okay, so there was no guarantee that they should have, and this is a case where you're really probing the result of the CFT, although the gravity computation gave you the impression that there was not much interesting going on.
How did you know a priori that you should match this gravitational calculation with Ramon ground states as opposed to Nova Shores?
That's an excellent question. I don't know. Because if it's NS, I would have written a beautiful one.
So the Ramon ground states somehow connect to
It's just because of
RR fields and
yeah. It's the index that I'm computing in the Ramon sector. Yeah, but
This is pretty simple relations, spectral flow relations.
yeah, but I definitely don't want to put that this number here is 1. Like the number here, so let me just be clear. So you might have, from the crossing kernel's point of view, like from just the general formula, you would have said, I'm doing this, like the only thing that I need to know is like coming from like the vacuum, the ground state of the theory, and you would have said, but the NS vacuum is unique. So then this contribution here should just be 1. So this is what I was calling rho naught, this ground state degeneracy. So you might have been misled to put there a 1. But if you do that, then you don't match it to this computation. This computation explicitly doesn't say anything about like, okay, fermions are periodic in this computation, but that's the only thing that you're saying about them.
so I should have asked this earlier, but zero modes from isometries, you mean collective coordinates of black hole?
No, well, I mean, technically speaking, I mean that when you compute a one-loop determinant, there can be 0 eigenvalues in that determinant. And so usually, like for the metric, they come because you have killing vectors. So that's what I meant by isometries. But then vector fields also can have like 0 eigenvalues and fermions as well. Scalars don't have the one-loop determinant never has a 0 mode associated to it. But yeah.
There the symmetry is broken by the black hole.
Yeah.
Right?
No, actually preserved. Yeah, so the near horizon of this black hole. So here I have to, so maybe in the previous example, just because I'm more fond of dimensions. So this 6 comes because you have 3 killing vectors of ADS2 and 3 of S2. And that's 6. That's it. That's why that number is 6 there. So that's why I call them isometries, because like, yeah, the near horizon is ADS2 times S2. And then you get those, that's what that number 6 here means. And this depends on like, yeah, in the gravitini multiplet, you have like some fermion 0 modes there. So yeah. So you're doing these computations in the near horizon region of the black hole. Okay. So yeah, so that's how it works. So also, just so you know, this regime was quite important to understand. And so now I'm done. I'll just conclude, and my conclusions are quite short. There's a lot of things to do, but then I was lazy and I just wrote a very brief conclusion. You can ask me afterwards. Good way how to chat with the seminar speaker. What else could you do? So I'll just summarize basically what it was happening. So basically here I was obsessing on trying to understand the meaning of 0 and -4 and trying to basically account for it in terms of these logarithmic corrections on these other sides. And so the thing that you should understand here is that how something becomes simple or difficult on each side changes. It's not conserved. So sometimes, like, for instance, there were cases where I showed to you here that things were very simple, that it was just the ground state that you needed to know about. But in those cases, I actually had to know what local contributions of massless fields were. And I illustrated for you a different example where there was no local contribution of massless fields, but you did have to. So here was kind of simple and easy computation to do, but then on this side, it became quite cumbersome and detailed, and I needed to know a lot about the CFT in order to get that same information. And so one thing that I'll leave you to chew on, and I know it won't come through immediately from this, but something that that is nice from doing these derivations that I think will have implications in higher dimensions and in other cases is that these coefficients here that I was extracting, in all cases, they basically don't depend explicitly on the charges of the black holes or the parameters of the modular forms. They were just like integer powers or fractions that were showing up in the expansions. Okay, so they're just like some rational numbers, but they don't depend on the state itself. Now, I can tell you offline of examples when you do this gravitational computation, and okay, in the examples that I presented to you, the answer was 0 or -4, but there's other black holes, even if they're supersymmetric, where this number actually depends on the ratios of the charges. So challenge for you, please tell me a CFT where you would get that. I have not been able to find a CFT that has a logarithmic correction that looks like this. So with that, I'm basically done. Thank you. I hope you saw the light.
So the Jacobi form structure comes from the symmetric orbifold match between ADS3 or
Yeah, in a sense, so this is where I get inspired by papers of Pear from back in the day, but basically, well, the Jacobi forms come from like, yeah, this is why it was very natural to try to understand this match from the perspective of ADS3 CFT2, which is part of what's lingering behind all of this talk. And so it's because, it has modular properties, and we know from ADS3 that modular invariance is translated to large diffeomorphisms. So that's why these objects should be the right object to
there's
study.
no complete derivation. I'm
No,
trying
no.
to see what the logical connection.
No, it was just, so a lot of these black holes, so technically speaking, the black holes that I was putting as an example have an ADS2 times something. You can usually uplift them to something that then looks like ADS3 times something, and then I'm applying the rules of ADS3 CFT2. That's what I'm doing. So I'm just saying, basically, I'm giving a rule of like, if you start with a black hole in ADS2 and you think that it has an ADS3 counterpart, you should be able to interpret these corrections from the point of view of the CFT. So I'm not doing ADS2 CFT1 because that's too weird to do, but yeah, I'm doing basically. So the modular form is naturally associated to the fact that the black hole had somewhere an ADS3 factor.
And like the Chern-Simons couplings are important for the right weight. So
the Chern-Simons.
I mean the ADS3, the Chern-Simons coupling.
Yeah. So there's all sorts of ingredients. So when I wrote the maps, I didn't go into details, but all of these so all of this goes through quite a lot of the machinery of like, you could have asked me, why was delta 0 this combination of charges? And so here I'm throwing tons of things like under the rug, because otherwise we'll be here for like the whole afternoon, which I think nobody will appreciate. But basically, this is the central charge, or this is the ADS radius in units of Planck length. Yeah, so this is the ADS3 radius. And this will be like an energy of a BT-set black hole and angular momentum that you get to the BT-set black hole. That's basically, if you want to have an ADS3 perspective of what's going on. But the computations, the logarithmic corrections are done from like an ADS2 perspective. So you kind of zoom in and go down one dimension. So when originally back in 2011, these things were computed, the papers are written, like most of the papers like do a lot of work on like, okay, let's extract these corrections. And then they say, well, it's known for reasons that this is the generating function. And then they just see, yes, it matches, and they left it at that, but they didn't, which is great, like, we were all very happy that the corrections match, but I wanted a little bit more insight. I want to see what the patterns are, because there will be black holes for which I won't have this luxury, right? That we just don't know what the microscopic counting is. And so part of the agenda is like, okay, this is something that I can compute, but if I compute it, then how should I think of it as coming from something microscopic? How can I see that this thing will lead to an integer, right? And so that's part of like the last question that I was asking. I think those cases, and when you will see already when you're trying to quantize and do this gravitational path integral, that these things won't arrange themselves such that they resum into a Rademacher expansion. That was the beauty of some of these examples, that you expect this thing that's like, as you compute all the corrections, the thing will exactly give you an integer. But I think there's cases that you already see from how these coefficients behave that it just doesn't fit. And so then you will be concerned about, is this a UV complete theory of quantum gravity? But yeah.
Here you were trying to calculate the microscopic data that controls the low energy coefficient graph. Can I ask, am I entitled to ask a more fine-grained question as to which UV data controls the low contribution capacity speed, like zero, but separately?
That I don't, and these examples kind of tell me that it's kind of awkward to do the split. So for instance, in the previous case where you had both, I can't tell you that this one corresponded to this one, and this one corresponded to that one. I don't know how to do that.
It's a bit too much to ask.
It's a bit too much to ask, and I think it might be. I think there may be cases. It's just it's a problem of like how you set up the computations from the gravitational point of view, because you really, when you compute log of A, the way the argument goes is that it's really log of lambda that you're computing. And so you erase the sensitivity to Q and P independently from the path integral point of view. Because you're trying to argue why the log comes from one loop determinants, and for that you need to try to uniformize what is the behavior of the eigenvalues and the determinants, and do that uniformly. So in gravity, I'm being a bit schematic here, but it's not, and that's why I didn't write down like, oh, you get a log of Q plus a log of P. If I had that, then your question like would make sense here, because here I did have like a log of delta and log of delta naught. But at least the way these computations are stood up is such that everything kind of like scales like in the same way, and it's technically log of lambda. Yeah. No, but that will be super nice to have that split, and then see like, you always see that the zero modes map to this part of the CFT spectrum, or like the local contributions to this one. But yeah, right now I don't.